Okay, this was the first homework problem from chapter 15, and it reminded me there was something I meant to talk about in chapter 14, and I forgot. So you can read about how to transform circuits from the time domain into the S domain, or I think Dr. J said the frequency domain. You have an option with both inductors and capacitors to do a series connection with a voltage source or a parallel connection with a current source. And I tend to like things in series. So I did that for the inductor, but for the capacitor, it was really hard because when you want the voltage along this whole branch and there also is a voltage source on it, the voltage division just got to be kind of a pain. So how I did it then was the series connection for the inductor and a parallel connection with a current source for the capacitor. And so here's my circuit in the S domain. And then I'm not sure if I got the right answer. I'm not sure if there's a more efficient way to do it, but I used nodal analysis. So there were two unknown voltages. The V naught, that's what we're trying to find, the voltage across the capacitor. And then at that kind of middle node, I called that V1. So I did nodal analysis, and then when I solved for V naught, I got this expression right here. I'll go to my other document that shows you the work. But if I'm not going to walk you through it because it's just time consuming, so you can pause the video and copy it down if you don't understand. You should try to get here by yourself, right? And then see if you can't, where you made a mistake. Okay, so when I did nodal analysis at the V1 node, here was my equation. I tried to simplify it kind of as much as I could. So I did a bunch of algebra to get it simplified. And then here's my equation for the V naught node. And again, I tried to do a bunch of algebra to get it simplified. So I solved for V1. So I got this expression in terms of V naught. Substituted it back in for that V1. Did a bunch of algebra. So I'll go here. You can pause if you need to get a closer look at those three lines. And then I want to isolate V naught, so I multiply both sides by the reciprocal of what V naught was being multiplied by. So here was the original right-hand side, that's right here. And then the next fraction is the reciprocal of what V naught was being multiplied by. And so you can see that I did some cancellation there. The 2's canceled, the 10 to the 4's canceled, one factor of S canceled, but one stayed. So there is what it simplifies to. And remember, every polynomial can be factored into linear and quadratic factors. If you have a quadratic factor, it is so much easier to factor it than it is to do the completing the square. So I would say try to factor it. You can always factor it over the complex numbers, but to me, it's easier to deal with completing the square. So first I just check to see, does it have any real roots by checking the discriminant of the quadratic formula, the b squared minus 4ac. I got a negative number, so it doesn't have any real solutions, so that quadratic can't be factored. Okay, so that means my denominator has two irreducible factors, so it can be decomposed into two fractions. Okay, so the first one is just a over the first factor, which is s, and then plus something over the second factor, and since that's quadratic, remember the numerator is linear, bs plus c. And then I multiply both sides by the LCD to clear fractions. And then there was one nice value to plug in, and that's s equals 0. So I just get the 2 times 10 to the 9th equals a times the constant of that, 4 times 10 to the 8th, the whole bs plus c is gone. So a was 5. For the second and third, there's not like a super nice number to plug in anymore. And I wouldn't plug in like 1 because you're going to get your 3 and then your 4 times 10 to the 8th. That is going to disappear. So I made a choice to plug in 10 to the 4th because then every term is about the same size. And then I plugged in negative 10 to the 4th. So I'm just going to bring that up. Again, you can pause and copy what I did, but I ended up with b equals negative 12 and c equals negative 210,000. So then I can write the partial fraction decomposition. I might have that down here. I'm just gonna copy and paste. I'll be right back. Okay, I lied. I think I'm just gonna walk you through it. And if you wanna copy some of the writing down, you should just pause the video. So here's my a over s plus b s plus c over that quadratic factor. And remember, if you can't factor the quadratic, the only option is to do completing the square. You don't want s squared to have a coefficient besides 1 for completing the square. So here I factored out the 3. And so if you factor out the 3, then you just get s squared and then divide the other 2 terms by 3. And then all I did was, instead of leaving 3 in the denominator, kind of thought of bringing a 1/3 up to the numerator, or just did negative 12 divided by 3 is negative 4, and negative 210,000 divided by 3 is negative 70,000. And then I completed the square in the bottom with what was left inside parentheses. So to complete the square, remember you do s squared plus this. And then the thing you have to add and subtract is you take the half of the middle coefficient and square it. Well, half of the middle coefficient would be 25,000 over 3. And then you square that. Okay? So you would add and subtract that. When you add it, that allows you to write the first 3 terms as this perfect square. And then we already had plus 4/3 times 10 to the 8th. And then here's the subtracting part of it, right? So I added and subtracted 25,000 over 3 quantity squared. Then, okay, so remember when you go to the table and you have like s plus a squared in the denominator, then if you have an s in the numerator, it has to be s plus a. So you can't just have s over s squared or s plus a squared. Whatever the expression in s is in the denominator, you have to have that same expression in the numerator. So since I have s plus 25,000 over 3, then this s right here also needs to be replaced with s plus 25,000 over 3. So I'm just gonna leave that -4 out in front, parentheses, add and subtract, which is what you see me do in this next step. So I have S plus 25,000 over 3 minus 25,000 over 3. Then I kind of leave this part alone, and then I'm going to distribute the -4 to this term and combine it with the other constant. And then in the denominator, I have the S plus A squared plus those other two constants. So all I did was combine them. And that gave me that, oh, what is it? 63,888,888.8 repeating. So that was when I combined the two constants at the end in the denominator. But then remember, also, we want the denominator to be of the form S plus A squared plus omega squared. Oops. Right? So I just want that second number, I want to write it as the square of a number. So I just took the square root of that 63888888.8, and it was, you can write that as 7,993.0525 quantity squared. So the stuff inside parentheses, that's your omega. Okay. And then this is your A. Okay, so rewriting. 25,000 over 3 is 8,333.3 repeating. The 5 over S just carries it. You don't ever want to change that. So I split that second fraction up into two fractions. One that has the S plus A in the numerator. That's the one that goes with cosine. And then the other one, the sign has omega in the numerator. So I want the part with S plus A in one fraction, and then the part with the constant in the other fraction. Okay, so when I combined the constants in the numerator, the ones that I have kind of the arrows in yellow, so the -4 times -25,000 over 3 gave positive 100,000 over 3, and then subtracted 70,000, and that gave me this minus 36,666.6 repeating. Okay, so that was the constant kind of left over in the numerator. The denominator is the same as it is in the first fraction. But remember, we want omega in the numerator. So I'm going to force it. So what I do is I multiply and divide by omega over omega. And so then I kind of make two fractions out of this. One with that big denominator and omega in the top, and then put the other two constants together and just do the division, and I got 4.5873. Okay, and so then when we take the inverse Laplace transform of that, so this V naught here was in the S domain, or I think she said frequency domain. Now, so I am taking, I didn't show the step, but I'm taking the inverse Laplace transform of both sides of the second to the last line to get us back into the time domain. So now this V naught is in the time domain. 5 over S, I would bring the 5 out in front, and then the inverse Laplace of 1 over S is 1. Right, the second row of our table. And then I manipulated this fraction so it matched the cosine. So this one right here, right? It was the S plus A over S plus A squared plus omega squared. So e to the negative at cosine omega t. So e to the negative, my a was the 25,000 over 3, or decimal form, 8,333.3, the negative. So e to the negative that, and then cosine omega t. And then the second fraction I manipulated to be like the sine part of it. And I just put that constant, the 4.5873 out in front. And then there's the e to the negative at times sine of omega t. So this problem put a lot of stuff together. The partial fractions, completing the square, the shift in the S domain. So that had a lot of it. So I think that's it.